For decades, cosmologists had a model that worked. It explained the Big Bang. It predicted the abundance of hydrogen and helium in the universe. It accounted for the clustering of galaxies across billions of light years. Scientists were confident. The broad strokes were settled. Then, in the 1990s, two teams set out to measure how fast the universe was expanding. They used different methods. They expected to get the same answer. They did not. One team got a rate equivalent to galaxies flying apart at about 46,000 miles per hour per million light years of distance. The other team got 54,000, nearly 8,000 miles per hour faster. For years, scientists assumed someone had made a mistake. Then James Webb launched, and it looked at the same stars with the sharpest eyes ever pointed at the sky. And it confirmed the higher number. No mistake, no blending, no measurement error, just a universe that is expanding faster than our best model says it should. This video tells you what that means and why it changes everything. Subscribe to Space Aquarius and let's begin. Let's start with the number that broke everything. It is called the Hubble Constant. It measures one specific thing: how fast the universe is expanding right now. Not in the past, not in some theoretical future. Right now, today, at this moment. You would think a single number like that would be straightforward to pin down. Two teams, two methods, same universe, same answer. That is how science is supposed to work. It did not work that way. There are two main methods for measuring the Hubble constant. The first method looks backward. The European Space Agency's Planck satellite spent years mapping the cosmic microwave background, the faint afterglow of radiation left over from when the universe was about 380,000 years old. From that map, physicists extracted the conditions of the early universe, plugged them into the standard model, and ran the equations forward nearly 14 billion years to predict how fast the universe should be expanding today. The answer they got was a rate equivalent to galaxies moving apart at about 46,200 miles per hour for every million light years of distance between them. Think about that in terms you can picture. If two galaxies are 1 million light years apart, they are moving away from each other at 46,200 miles per hour. If they are 2 million light years apart, they are separating at twice that speed. The further apart things are, the faster they are flying apart. Clean number, tiny margin of error, high confidence. The second method is more direct. Adam Rees, a Nobel Prize-winning physicist at Johns Hopkins University, and his team used a technique called the cosmic distance ladder. They measured the distance to nearby pulsating stars, called Cepheid variables. These are stars whose brightness fluctuates at a rate directly tied to how luminous they actually are. Measure the pulse, calculate the true brightness, compare it to how bright the star looks from Earth, and you have a distance. From there, they stepped outward to galaxies containing both Cepheid stars and a specific type of exploding star called a Type 1, a supernova. These supernovae are useful because they all explode with roughly the same peak brightness. Once you calibrate them with Cepheid stars in the same galaxy, you can spot them in galaxies hundreds of millions of light years away and calculate how far those galaxies are. Combine that with how fast they are receding, and you get the Hubble constant. Rees's team got a rate equivalent to galaxies moving apart at about 54,000 miles per hour for every million light years of distance. Not 46,200, but 54,000. Nearly 8,000 miles per hour faster per million light years than the standard model predicts. That might sound like a rounding error. It is not. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% between two completely independent methods is enormous. It changes the age of the universe. It changes the size of the observable universe. It changes the rate at which galaxies are separating. It potentially changes the nature of the dark energy that has been pushing everything apart since the late 1990s. At a 2019 conference, Rees asked David Gross, a Nobel laureate in particle physics, whether the field should start calling this discrepancy a problem. Gross corrected him. He said they should not call it a tension. They should not call it a problem. They should call it a crisis. Now here is where James Webb enters the story. For a while, scientists assumed someone had made a mistake. The most popular theory was that the Hubble Space Telescope, when measuring Cepheid variable stars, was sometimes blending the light of nearby stars together. The stars were too crowded. The images were not sharp enough. That blending was making the Cepheid stars appear brighter than they truly were, which would make them appear closer, which would push the Hubble constant higher than it should be. If you could clean up that blending, the argument went, the tension would relax. So Rees pointed the James Webb Space Telescope at the same stars. James Webb orbits the Sun about 1 million miles from Earth. Its mirror spans 21 feet across and is coated in gold. It collects infrared light with a sensitivity that makes Hubble look like a pair of reading glasses. If any telescope could settle this, it was James Webb. The expectation among many in the field was that James Webb would gently deflate the tension. Its sharper vision would reveal the blending, correct the distances, and bring the Hubble constant back into line with the standard model. Some astronomers were already drafting the obituary for the crisis before the data came in. James Webb confirmed Hubble's numbers, not approximately. Almost exactly. The Cepheid stars looked the same. The distances held. The expansion rate stayed at the higher value. In early 2024, Rees's team published a paper in the Astrophysical Journal Letters announcing that they had now spanned the full range of Hubble's Cepheid observations with James Webb, extending all the way out to a galaxy called NGC 5468, about 130 million light-years from Earth. 1,000 Cepheid stars across 5 host galaxies of 8 supernovae. The conclusion was unequivocal. Measurement error could be ruled out with very high confidence. Rees put it simply, with the errors eliminated, what remains is the real and exciting possibility that we have misunderstood the universe. But the Hubble tension was only the first crack. Because almost as soon as James Webb started observing, it found something else, something that the standard model had no room for. Galaxies in the early universe that had no business being there. Not small, dim, infant galaxies, which is what the standard model predicted at those distances. Massive ones. Galaxies seen as they existed just 500 to 700 million years after the Big Bang, some of them rivaling the Milky Way in mass. A galaxy that took our own neighborhood 13 billion years to build had apparently assembled itself in under a billion. Astronomers ran the numbers. To form galaxies that heavy that fast, nearly every available atom in their surrounding environment would have had to convert into stars. In a normal universe, that conversion rate sits around 10%. 90% of the gas just never gets around to forming anything. These galaxies seem to be running at 100% efficiency. Physics does not work that way, not in any model anyone had built. The initial reaction was alarm. If galaxies this massive really formed this quickly, then either our models of galaxy formation are deeply incomplete, or the standard model of cosmology itself needs revision. And then James Webb found something even stranger. In early 2025, it captured an image of a massive spiral galaxy that existed within the first 2 billion years of the universe. Spiral structure takes time to develop. It requires relatively calm, orderly growth, not the chaotic merging you would expect in a young universe. The astronomers who discovered it said the galaxy either assembled its mass in an unusually neat way, or it formed most of its stars in place without the violent collisions that typically build large galaxies. Either explanation challenges conventional thinking. So here is where the science honestly stands. The standard model is not dead, not even close. It still explains the cosmic microwave background with extraordinary precision, It predicted the abundances of hydrogen and helium in the universe. It accounts for the clustering of galaxies across billions of light years. No competing model can match its track record. But it is developing fractures that were not there a decade ago. The Hubble tension refuses to go away. The early universe is producing galaxies that are bigger, more structured, and stranger than expected. And the nature of dark energy, the 68% of the universe responsible for its accelerating expansion, remains a placeholder name for something we cannot identify, measure directly, or explain. There is even a second, quieter tension that most people have not heard about. It is called the S8 tension, and it concerns how clumpy the universe is. The Standard Model predicts a certain amount of clustering in the distribution of matter across space. When astronomers measure that clustering directly, they consistently find slightly less of it than the model expects. Rees has called it the little sibling of the Hubble tension, two cracks in the same wall. And here's the thing about cracks in physics. In the 1990s, the field nearly collapsed under the weight of a different contradiction. Measurements suggesting the universe was younger than its oldest stars. That made no sense. The stars could not be older than the thing they lived inside. Then came the discovery that the expansion of the universe was accelerating, driven by dark energy, and the whole picture snapped into focus. What looked like a fatal flaw turned out to be the shadow of something enormous that nobody had seen yet. That is the thing about crises in physics. They feel like endings. They almost always turn out to be doors. New instruments are coming. NASA's Nancy Grace Roman Space Telescope will conduct wide field surveys designed specifically to study dark energy. The European Space Agency's Euclid mission is already mapping the geometry of the universe on a scale no telescope has attempted before. The universe is not broken. Our map of it is just incomplete. And the next version, whenever it arrives, is going to be stranger and more beautiful than anything we have drawn so far. If this video got you thinking, subscribe to Space Aquarius so you do not miss what comes next as the data keeps coming in. Leave a comment and tell me which discovery unsettles you more, the Hubble tension or the galaxies that should not exist. And share this with someone who thinks we already have the universe figured out. They need to see this.